Okay, so thank you everybody for joining. So today I will be talking about the NanoIR nanoscale infrared spectroscopy system that has been recently installed in the SPID facility. It is basically by the side of other AFMs that you use on a regular basis. So I will touch base some of the applications, some of the capabilities that we have on this new system, and it will be soon open to training, maybe in a couple of weeks. And then I will also send a notification about the different applications, the capabilities, and the unique features of this system. So before I cannot move. Okay, before I start, I always show some of the old scanning probe microscopes, so basically what they have done like almost 40, 50 years ago, then we are just enjoying the fruits of their hard work. And then you can see to what level the new instrumentations and techniques have been developed. But the core principle is basically the same of scanning probe microscopes. So this is one of the oldest scanning probe microscopes where they have physically looking at the optical microscopes and looking at the probe sample interactions, manually they are moving the sample closer to the samples and try to scan it. And then you can see this is a rough configuration of that first scanning tunneling microscope that was designed in IBM Zurich. And then you can see they got the first, they take like, use a scotch tape and take the graphene monolayers and then get a atomic structures on that. And then looking from a closer perspective, you can see how he's basically putting a probe inside the probe holders, and then there's a sample opposite to that, and how we can manually move the piezo staves to make sure that the probe touching the samples and the current is flowing and they're getting these things. And then this is that old microscope in the British Science Museum. So it just looks like a normal spacecraft, but this is pretty unique. And then whenever you go there, you can see it there. And then traditionally, it has been known to many people here that scanning probe microscope is just to do a surface profile, topography, roughness measurements, 3D imaging, and that's all. But now it is not the case now with the recent advancements. Now the scanning probe microscope is entering into this more functional imaging, like mostly they are focusing on chemical imaging, electrical imaging. So that cannot be done with other techniques. It's a multimodal system. So you require a lot of microscopy and techniques to do these things separately. But here you can do all these multitasking type functional imaging on a single piece of instrument. So the normal scanning probe microscopes, bring you the topography, mechanical, electrical, magnetic properties. It's a pretty well-known phenomenon. And then people have been using it for the last 20, 30 years. And then we also have these capabilities in our facilities for the last 20, 30 years. But now, for the last few years, we are truly moving towards more quantitative and more functional imaging, where people can take the advantage of a high resolution AFM imaging, along with they can identify the different aspects of their samples. So, but it lacks chemical sensitivity. So you can see in the images, you can see a nice electrical carbon topography, but electrical map of a carbon nanotubes. You can see some nice cancer cells and all those things. They look fancy, but we are moving more towards that. So before I start something with NanoIR, I want to quickly touch base with one of the chemical analysis system we have already from last year. It's called the tip-enhanced Raman spectroscopy. So that's a pretty powerful tool. So normally in the Raman, you can do a chemical mapping or chemical analysis, but the resolution is limited to a few microns depending on the spot side of the laser. But In this case, we integrated the system with the scanning probe or atomic force microscopes. Then we can introduce the tip enhanced Raman spectroscopy. Here we use the conducting probes and create basically, you can enhance the electric field at the top of the probe. So basically you are creating a nanoscale hotspot, and you can significantly enhance the signal by a factor of 5. So, and then also at the same time, you can also go down to resolution of few nanometers. It's based on Raman is based on an inelastic scattering. So mostly I will explain the difference in a couple of slides. Here you can see an example of, the TERS system is basically scanning a carbon nanotube. And then you can see a carbon nanotube with different, different band structures in the chemical mapping. At the same time, you can see the spectrum. And this is one of the other examples of a third system in a 1D material application like nanotubes, nanowires. Here you can see a chemical TERS map of a carbon nanotubes, where the different color contrast indicates the different defects within the carbon nanotubes or different bands, D bands, G bands, 2D bands. So you can do it these things here. TERS is little complex techniques. It requires a lot of practice and a lot of experience to do that, because most of the practice involved is basically how you properly align the laser on a probe. Because if the laser is not properly aligned on a probe in a right way, then basically the signal enhancement will not happen. Okay, so now what is the difference between TERS and infrared spectroscopy? They are same or different. So basically, TERS is based on a inelastic scattering between the incoming photons. They interact with the surface, and then basically inelastic scattering that gives information about the sample symmetry. It can give the information about the chemical bonds, symmetry, mostly applicable to non-polar molecules. Inelastic scattering of light. In the case of a nanoscale spectroscopy, IR, here basically it based on the thermal expansion, because if you're using infrared lasers, basically you can just direct toward the sample, and then the sample absorbs the lasers and it results in the thermal expansion of the material. And that thermal expansion of the material basically changes the mechanical forces between the probe and samples. And on the basis of that, you can get the IR spectrum. Okay, because of the size of the probe, the resolution goes down to 510 nanometer in this case, as compared to few microns in the case of a FTIR techniques. Okay, so Raman is mostly focused on basically determining basically determines the symmetry of the molecules, or like symmetric molecules basically can easily identified in the Raman. In the case of a NanoIR, mostly it's a chemical bond information, non-symmetric molecules, polar molecules. So you can do these things in that. In the Raman, the enhancement mechanism is based on plasmonic enhancement, using a metallic probe. We use a very special probe, often coated with gold and silver, and that can amplify the electric field. Okay, and that results in a signal enhancement by the factor of 5 or 7. The case of nano IR is basically the thermal absorption. Okay, and that creates oscillations, and then the probe is there to detect those oscillations. The TERS is, as I said, you can use nanostructures, semiconductor, graphene, carbon nanotubes. The TERS has a limitation that the sample thickness has to be just a few nanometers. Okay, so the sample prep is basically very critical in the case of TERS mapping. And then in the case of nano IR, there's no limitation as such. The depth resolution is like 100 nanometer. It can go up to 100 nanometer with a contact mode. TERS, and basically the tapping mode IR imaging is more kind of a surface sensitive. It's not limitation to just semiconductors. You can do a lot of proteins or biomolecules, polymers, because most of these proteins, polymers, they nicely absorb the IR. Okay, So that's the difference here. Now the system we have is the dimension Icon NanoIR system. So I will give a little introduction about that. Then I will discuss, what type of systems we have, what different modes and options we have on the system. And then this technique is also called the photothermal AFM-IR because basically you are using those pulses and then you can basically thermally expand that material. So it's a photothermal AFM also. In the conventional FTR spectroscopy, you can see here, they provide the chemical resolution. We have that system in the CAC2 facility, but they have limited spatial resolution, many microns. There is a little improvement over that techniques in the last couple of decades, but with this invention of this NanoIR or integration of this IR system with the AFM, the resolution is really pushed down to few nanometers. Since the NanoIR is in the market, this is one of the advertising slide from Bruker. So basically, the publication is coming almost every day. And then this system has been installed at few different locations. Most of the application is polymers, life science, thin film, semiconductors, 3D materials, and plasmonics. So basically, we are not limited here to a very specific sample preparation. As long as the AFM can get a nice topography image, we can get IR spectrum. But unfortunately, we cannot do in liquids, so that's one of the limitation here. So in the case of IR or the photothermal AFM IR spectroscopy, an IR pulse arrive at the sample surface, and then the sample absorbs that and heats up and expands. So when there is a thermal oscillations of the sample at the pretty localized tip sample interaction, it creates the mechanical forces and disrupts the cantilever interaction, basically modulate the cantilever oscillations. And then the magnitude of that oscillation is proportional to the absorption coefficient. Okay. That's the basic principle of this system. Here also we use the normal silicon probe. In the case of a Raman TER system, we use a very specialized probe. And then the probes itself are a little costly, but here we just use the traditionally gold-coated cantilevers. They are not that costly. There's no like a standard specific probe for that. It's a pretty normal probe. It's a one technique, but there are two ways you can investigate your sample. One of them is basically you can do a spectroscopy, so where you can keep the probe fixed in space and scan the IR wavelength. Okay, then you can have a multiple sample can be investigated, or multiple variations in the samples can be investigated at once. And then another option is you keep the IR wavelength fixed and then scan the sample. So you can do the chemical mapping. And that mapping also, you can do at high resolution, but can be done only at a very specific wave number. And then whenever in the AFM, there's always an issue when the probe is interacting, when any oscillating probe interacts with the sample, what happens, depending on the density variation of the sample, there's a shift in the frequency. The shift in the frequency can be more for softer materials compared to harder materials. So how we know that whatever changes or variation in the IR imaging we are getting is basically a true sample interaction, not from other mechanical variations like a stiffness or contact area and all those things. So here the system use the phase logged loop. So in this case, what it means that if there is a probe is interacting with different regions of the samples which has a different density variation, for example. So there is a shift in resonance. So what happened, the phase logged loop, it just get activated and try to maintain the cantilever resonance. So make sure that we are getting the true chemical information just at the tip sample interaction interface, not the variation because of the maybe thermal, mechanical, maybe contact area differences. So on the left, you can see the image is basically without phase log loop, and on the right, which is much more clean, nicer image, is with phase log loop that represents the true chemistry true chemistry of this imaging technique. So the dimension IconIR we have is basically pretty much, the tool is pretty much the AFM that you are using. It's a 8-inch stage here, but in this case, it's exactly the same, the high performance spectra with FTI correlation. You can go down to even 5 nanometer resolution, spatial resolution in the case, and also the spectral resolution in the case of a tapping mode IR. It's a monolayer sensitive. And then you can also do a correlative microscopy. That's one of the advantage here. That means you can do IR spectroscopy, you can do chemical mapping, you can do a topographical variation, but at the same time, you can do electrical properties measurements, magnetic properties, and photoconducting properties, and all those things. So every other techniques possible you can do at once. So that's called the correlative microscopy. And that it also has a mirror view. So that means, whatever area that you can identify in an optical image, you can point and shoot, and exactly the probe go there and take the spectrum. This is the stage that we have. It's a larger sample platform, so pretty high precision, and it's pretty easy to use. Basically, most of the AFMs you have seen in our labs, they are pretty straightforward, semi-automatic, easy to use. So the icon stage is also pretty much similar to whatever the normal icon AFMs we have. Except the fact that we have a PI stage at the bottom. So that means here you can also move the stage. In the case of a traditional icon system that we have, we cannot move the stage, okay? We can only use the tip scanning. But here you can also do a tip scanning, and you can also do a stage scanning, okay? So that means you can do chemical mapping, or you can also do a spectral imaging where you can fix the location of a sample and then scan across the broader IR spectrum. it has a closed enclosure, and then we are purging this enclosure with air. So that means basically, you have to keep the humidity level pretty low so you can minimize your background noise. At the same time, there are certain logs or options or protections here. That means when the door is open, the laser will turn off. So basically, it's a IR laser, so we cannot just directly expose our eye with the IR laser. So that's what this protection is there. And when the hood is open, the IR laser is shut down. When the hood is closed, the IR laser is on. Okay. And then the other unique advantage of this closed chamber is that this is an environmental chamber. You can pass the nitrogen gas, you can just use the other gases, because a lot of users comes to me and say, okay, I need the nitrogen ambient, I need this ambient. So basically that option is here. And then we can, basically the chamber is pretty small, so we can easily keep the ambience according to your sample applications, okay? So that option is here. This icon system can do a traditional AFM imaging also, means you can do all these electrical, mechanic, and all those things along with the IR imaging, but mostly we'll focus here in the beginning, mostly on the IR setup for this system. We have one of the question initially was that, what is the spectral range we have? So right now we have the left one, the hyperspectra QCL 764 to 1800 wave number. So most of the fingerprint region is within that. The middle one is not that important, and in the future, things depends how the things goes. We do have plan to buy the other option starting from 2700 wave number to above. So that is a plan that we acquire this laser in the future. But currently we have this range, 764 to 1800 wave number. Now there are a couple of things, conventional, the different options we have on this system, conventional AFM-IR and resonance enhanced AFM-IR. So conventional AFM-IR is basically the contact mode. You bring the probe in contact with the surface, You shine your lasers and there is thermal expansions, and basically you can read out those oscillations. With the conventional contact mode AFM, the resolution is few nanometers. You can go to a depth of 100 nanometer, means if you have multi-layer films, go down to 100 nanometer, you can get a spectrum from different layers. But here, the signal intensity may not be that strong, so that's why we do have the option of resonance enhanced AFMIR. So basically, we scan when there's a thermal expansion of the materials, we can scan the frequency range and we can find the contact resonance of the cantilever. If we can excite the contact resonance of a cantilever, we can amplify the signal. So basically, there are two ways you can do that with but the resonance enhanced AFM-IR is the best option for us because we can basically amplify the signal. Then there's also a tapping mode IR, so which uses the conventional tapping mode cantilevers. It's all metal coated. In the case of tapping mode, basically we excite the cantilever at its resonance frequency, and then basically we can implement the phase logged loop on that option. So the tapping mode is, as you have seen, that basically it has a better resolution than the contact, and basically it is also more friendly for softer materials. Like if you have very soft material, then because of the lack of shear forces, the probe will not scratch the surface and all those things, as compared to the contact mode, which is good for hard materials, but when it comes to soft materials, use the tapping mode IR. It's a non-linear tip-sample interaction, so it's more surface sensitive. If you want the IR signal from the top layers and from the surface, then tapping mode IR is an option for us to go. Then you can see the resonance enhanced AFM-IR signal to noise ratio is a metal coated tape. Now, basically, it enhances the nanoscale IR spectroscopy chemical imaging on the sample as thin as 5 nanometer. Then we can also do a hyperspectral imaging. Rather than doing a chemical imaging, you can basically scan the whole band of this IR spectrum, and then you can do simultaneously the chemical mapping that you can do at a fixed wave number. But in the case of hyperspectral imaging, you can just draw a line and you can go pixel by pixel. You can draw a line across the different regions of the samples and you can get a different IR spectrum. So that options we have. This photothermal AFM has a different applications. I will just show you a few examples. You can do polymers, life science, cells, proteins, because proteins are very friendly to most of these IR bands, from 1200 to 1500 wave number. I will show you example of environmental, geoscience, cultural heritage materials, pharmaceutical applications, where you can see how the drug is delivered or not, material research, solar cells, perovskites, battery applications. There's a wide range of application. One example here is basically this polystyrene, this PMM block copolymers. On the left, you can see a topography. Then in the middle, a little magnified topographical image. On the right, you can see the spectrum taken at a fixed wave number 1730, which highlights the PMMA spares which are embedded in this polystyrene matrix. So you can pretty easily identify those pairs at a fixed wavelength. And then you can go. Then this is another example of polystyrene and unload of polymers. So basically you can see a chemical IR signature, the middle, top and bottom at different wave numbers. So you can get a different contrast based on the dominant, the molecular interaction at those wave numbers. At the same time, you can get the mechanical information, modulus information, Kelvin probe, whatever the other type of microscopy techniques you want to do that. So this is the unique advantage of this system, that you can do a multimodal functional imaging at the same time, and all are quantitative. Basically, you can calculate those values. Then it comes to the biological application, amyloids, they are basically responsible. They are insoluble protein fibers, mostly responsible for these neuro diseases like Parkinson's, Alzheimer's, They can be in the form of monomers, which are solubles, but they can be, in the form of the fibers, insoluble fibers. Okay, so when you do a normal topographical AFM, you can see on the left topographic images, but the IR images, then you can scan at a different wave numbers. You can easily identify which are monomers, which are oligomers, which are basically the fibers. So you can identify these things pretty high resolution. So this is a nice application. The breast cancer cells and other applications where you can see when the cancer is progressing, basically, the estrogen is more dominant. So you can see the control and the MCF7 and MCF7 incubated. You can see a little two smaller bands, A1 band, E bands. So that indicates, the estrogen level is rising. So basically, you can have direct application on these biomaterials. This is one of the examples of meteorites, where you can identify the different mineralogy and if it is organic contamination or not. This is one of the examples of two meteorite samples here. Then you can see the top left image, which is AFM map. The top is AFM map. On the bottom right F, you can see a different color contrast. So basically the lower part, the reddish area is 720, which is mostly it's carbonates. Then 1450, some other types of materials. 1040 basically scan wave number is silicates, SiO bond stretching. So basically it indicates silicates. Then you can see, you can identify the different, 720 is mostly, 1450 is mostly the organic contaminations on these meteorite samples. So it has a direct geological application, so you can do that. And then the last, this is, you can see the liposomes here. The liposomes mean nanoparticles. So liposomes are mostly used as the drug carriers. Okay. And then they are basically, this is like a chemotherapy drug, they encapsulated in the liposomes, and the liposomes are drug carriers. They can also minimize the effect of these drugs on the other parts of the body. But when you encapsulate these drugs in the liposomes, you can identify these things with NanoIR. So rather than doing a cross section, TMs and LCMs to identify these things, you can directly use the NanoIR and identify those encapsulated drugs. So it's a direct, unique application for therapeutic applications. Then the last is a high performance spectroscopy, and then you can get a sub-nanometer chemical imaging. You can see the different components of these polymers, compositions. Scanning at a different wave numbers, you can get a different contrast. So I think that I end here, but this system is available now. A little hiccups in the beginning. So now the things have been fixed. So we will just spend a couple of weeks ourselves to get used to the systems, and then we can open this system for training from October 1st. So those who are interested for training, they can apply for training. This system is a new core. And then this system is located in AG71 of the AB wing in Nuance Center. And then this is a pretty unique piece of system. So I invite all of you to come and use this system. Thank you.